Yes, okay, we can start. So it's hi, I think everyone can hear me now. Still. Okay. So I guess I can check back. It's like two weeks ago. So I think I lost track of what we are doing, but I checked back the data that what we stopped is where hypothesis testing, right? We basically finish everything up to the hypothesis testing, and then the t-test is over, right? So I guess the main thing is to start from lesson 4, right? Lesson 3 we have done, right? Is it the case? I think that's the case, right? We finished everything up to lesson 3, so it's a lesson 4. But let me very quickly review what we have been doing, because I mean, we have been stopping for 2 weeks, and I guess most of us will forget what we have done, right? So very quickly overview what we are doing so far, right? And I guess you've done the assignment, you know what we have been doing in the first few chapters, right? Especially chapter 1 is telling about how the data is being born. That will be an important thing that you would need to do when you do the project. And the lesson 2, we learned the main thing is to understand how to summarize the data, right? And to understand what the data is there, right? They learn summary statistics, we learn graphics, we learn correlation coefficient, we learn mean, median, all sort of stuff, right? And after that, lesson 3, which we covered 2 weeks ago, learns the idea that how you can extend the knowledge from the data, right, is about 2 things. One is being the estimation, the other being hypothesis testing, right? Estimation means that based on the information on data, you try to extend the knowledge to the area we don't have data on, right? For example, about stock market, we look at the past price history to extend to the future price prediction. Or in terms of IT solution, you're thinking about the traffic flows or the user behavior in your website, how it extended to the future, right? That, or you try to figure out something like more sophisticated is you try to see if you implement a new feature in IT system, how it changed the whole system structure, right? That would be rely on the things we do, right? That's estimation and hypothesis testing. So the goal today, actually, we will try to look at topic 4 and topic 5, right? That's what we are trying to do today. Would be trying to understand one of the main tools that we learn from the statistics. It's what we call the regression. Okay, and in this afternoon we talk about we call the simple regression, which try to understand how 2 variables, y and x, are related. Okay, and that would be simplest way to do is just y and x. And then after dinner, we have meeting at night. Then we will talk about more than one variable. Okay, it's a multiple regression. Okay, that would be extend to that. And after that, then we're done with the regression, and we'll do machine learning methods. So that would be, hopefully we do next week or the week after, we will touch on machine learning methodologies. Okay. What meet them all? Can I? Let me check out how can I set in the way that more. No. It's okay. Okay, so that would be That will be the goal of today, okay? I hope that is clear what we will be doing, right? Because the regression with technique that's so basic that a lot of machine learning method is extension to that, okay? And also regression turn out to be, later you will see, if you do your analysis based on data, turn out to be the most stable one, okay? If your data is not sufficiently clean, then actually regression will give you a more accurate estimate, okay? And when you have very big data set, actually the regression would not be too much different from machine learning. Machine learning is something good, but you would not expect that they are too much different. I mean, machine learning is good in the sense that if you extend to the area that we don't have much data, then machine learning may be able to teach us to a lot of stuff. But in terms of interpolating or try to talk about things we know a lot, then regression is likely to be the best tool you want to employ. Okay, so you'll be more clear later what do I mean by that, but you will later see what would be the best approach to that. Okay, so let's get started. Okay, and let's get started. Okay, the main idea of regression, as we said, is try to predict y based on x, okay? So that is the underlying, right? Because you want to understand the structure, how x and y related, okay? It doesn't mean x cos y or y cos x, okay? You just say they move together, okay? That is the main idea. And there are two goals you can see. The causal analysis, we want to say x cos y, right? Because at the end of the day, you want to do business decision, right? You want to say how change in x, which is your control, change to the y, right? Suppose you implement certain feature, right? You want to say this feature actually can help us to improve the performance, right? And that is something we want to establish, okay? Based on, say, your so a pilot study or your experiment or some other context, right? That we can estimate how x change on y, right? Or you look at a data in particular city, you want to extend it to nationwide. Well, this is very often we do in business, right? And that will be the first thing we want to do, and that is business decision. And actually, the next one is predictive analysis. Is we really don't care about whether x actually causes y, right? We want to say it's less ambitious goal, which just saying that I look at x and what will be the y? It was most likely y. We don't care about that. Maybe z that drive both of them, okay? And that is less ambitious. And you will see that machine learning method will be you will see a lot of predictive analysis. And when you do regression, that will the tool that will do causal analysis. Okay, this we will learn the causal analysis at the last two classes, and we will learn this maybe the next week. Starting next week, we'll do some predictive analysis. Okay, so that would be the main. And we are very modest today. We will focus on two type of variable. There's two variable here. Y is dependent, x independent, just historical name. Okay. And we try to use x to explain y. And for regression, in the literature, usually you would divide them into two different things. One thing is called non-parametric, which you may or may learn, but the one that usually you will learn is called the parametric method. Okay, the parametric method, that is actually something many of you would learn is 回归, right? Is linear regression, is sensing 回归, right? That is, you know very well is you have a scatter plot and you try to plot it, right? Because I think this is the one that you would learn most often like this, right? Is you learn regression, it's like you have a scatter plot, right? I hope everyone know what scatter plot is, right? And just suppose a data, right? And the data here is, let's see if I can use my pen here. Hopefully I can use. No, not working. So that's x here, that's y here, right? And because two variable, and then you can represent your data point here, right? So this data point maybe mean this 2, this 3, right? If your data is like x is 2, y is 3, then you have a point here, right? And Suppose there are many data points, right? Okay, look like this, right? And what's the regression? Regression is simply saying that I want to draw a line to summarize how X and Y are related, right? So basically it's a dimension reduction technique where your data is, oh, there are many people coming. There you have a data that has a very you have data that have many dimensions, right? So many data points, right? Can be a lot, right? Maybe billion or thousand, right? Depends on what you have. But at the end of the day, right, what you actually get is a line, right? For a line, then actually is very simple, right? You've learned from high school, right? High school math will tell you to describe a line, you actually do two numbers, right? Especially the intercept, slope intercept form, right? You only need to know two things. One is the intercept, right? What is the value of here? Usually called in our case called A here, right? Is what is the value of Y if X is 0? And the another thing that is called the slope called B, right? Which is saying that if you increase X by 1, how much Y will increase, right? Suppose this is the thing is, right? This is called slope, right? So if you have this kind of line, this line can be simply described by this formula, right? I mean, this is something that embarrassingly simple when you learn the undergrad, right, or high school. So we want to find a line, right, which is reducing the whole data to 2 points, right? I mean, basically all the analysis in statistics is reduction dimension where you reduce a very complicated data into a very simple model, right? In particular, this regression is reduced to 2 numbers. And how to design what is the best fit, right? What's the best line? Because potentially can draw many line there, right? What's the best line? So we would consider the classical way is just to minimize the vertical distance, sum of the square of the vertical distance. I mean, we'll talk about it more, but this is one way. And then if you consider more different way, what's the best, then you come up with different machine learning method. Okay, but the basic one we study right now, the simplest method is simply to find the vertical distance being the smallest. And the criteria we say sum of the distance smallest is looking at the vertical distance, okay, or the vertical distance, okay, and you square all the distance, okay, and add them all up, okay, will be what we call the least square method, okay. And as I emphasized, that many method, if you learn machine learning, but this classical method in statistics has a lot of nice properties. So that's why most of the analysis will be based on this style, okay, minimize the vertical distance. And some of you would ask, why vertical distance? Because potentially there are many distances available can be done. Yes, that is done in a lot of machine learning method, okay? In a classical statistical method, we focus on the vertical one. I mean, if you look at other, they would tell you, I think it's rich regression. They would tell you that instead of this, you look at the this perpendicular distance, okay? And there are many distances you can consider as well, but we'll focus on the vertical distance, square sum of the distance, right? Because some of you may worry, okay, why square? Why don't we do absolute value? There are many ways you can measure, okay? And there are many methods, but we focus on the most simple one, and there are very nice properties. So this is the most used in all the analysis, okay? So basically what we do today is to tell you that the basic study is to find the line that best fit the data, okay? And do note that there's a significance by just drawing a line, right? Because everybody knows how to draw a line. You learn it in the kindergarten, right? You can ask a kid, your cousin, give the data, that point there, find the line that fit the best, right? And there's a significance of being given a line here, right? Do note that although we say dimension reduction, right? We reduce the amount of data point to only 2 numbers. But indeed, when we say 2 numbers, it actually represent infinite number of data point, right? Because the line tell you that you give me this number, this is my prediction, right? And it holds for every x you give me, I'll give you the y, right? So it's not just reduction, it's extension to every number you propose to. You give me any number x, I will give you the y. Whether reasonable is another thing, but we are able to generate we use the finite number of data to generate a model that holds for everything that you give me x, right? So that is a big thing, right? Because we are trying to collapse the noisy or complicated data to a very simple model, but this simple model is going to apply to every general situation that we want to work on. Okay, so we simplify the data, but this knowledge will be generalized to everything that we want to study. So that is very important part because that is what data is about, right? Because you have a data we collect is trying to the small picture is going to extend it to a much complicated situation. Okay, so I hope that is very clear what we are doing. And no matter we have more complicated model, the same idea, right? Suppose I have exponential regression, then in fact will be very similar to what we're doing. Okay, but we'll be more clear about all this more extension. There are many different forms, but we focus on this in the first 2 hours. Okay, and besides this, we'll learn the other two methods, which is usually you only learn it in the master level or advanced undergraduate level. Is called the non-parametric method. In Chinese, it's called 非参估计, 非参模型. So what it means is, here we do have explicit parameter to estimate that, right? And non-parametric is like we try to not less rely on the form of the data. Okay, we do not try to make a assumption that how it looks like. Okay, looks a little bit loosely defined, but if we look at the method that we propose, then you will see what it's about. But that would be usually you would think, okay, what would be the appropriate analysis you should do is usually you would impose a non-parametric method and see how your result looks like, and that will actually give us some estimate, but that will give us how you should assume your functional form. Okay, so and you want your result to be robust to how you make the assumption, right? So you expect regressions to be similar to this method that you do other way around. Okay, and similarly, you expect later you learn machine learning method, you have some prediction from that model should not deviate too much from your regression model. So that would be the thing that I want to emphasize, because you will learn many methods, right? But at the end of the day, of course, you can do horse racing, right? But you still want to see whether these different model actually deliver related result, right? If your particular model deliver model very differently, then you have to be a little bit more careful. Is it you doing the right thing? Okay, so actually, I would expect your model for your project to be follow something similar idea. You would analyze in different model, then they give you similar result, then your conclusion is very robust, right? If you saying that, okay, your model give you this, but other model give you other thing, then probably I have less trust on what you're doing, right? You want different model to deliver similar idea, right? Just called robustness, right? Maybe particular model that actually perform the best, but otherwise you would try to have a second opinion, right? So this one, the first method we do is called the bin scatter plot, which we have learned in topic 3 already, lesson 3 already, right? If you still recall the example, maybe I think it's just like long time ago, but let me get out from here, right? If you remember lesson 3, we do one thing. Oh, not lesson 3. I think it's lesson 2. Sorry. I think that will be a last month. That will be a long time back for all of us. So if you still remember this graph, okay? And one thing we do is this, remember this case study is looking at how firm size related to their management score, right? And then we try to say the bigger firm is better. And look at this scatter plot doesn't seem to say what is the conclusion you get, right? And how do we get our answer there is we group them into 10 different groups, right? If you recall, the idea is we divide them into 10 bins. And basically, we look at the x-axis and divide the data set into 10 different parts, okay? And the way that we do is we don't assume the model there. Based on data, tell me that the first group, what is the average of the score, which is given the first group of X, was average of Y, right? And that would be our prediction of the model, right? Because in this case, Y is non-parametric because we didn't assume there's a linear relationship is linear, non-linear, anything. It's nothing, right? Basically just like, okay, within this group, what is the mean? Within this group, what's the mean, right? We don't make any assumption on that. Data tell us what it looks like, right? So this is actually, when we talk about this, we already give you a model, right? The model is being the following, right? Just let me rewrite this into the graph. Right? If you still recall, okay, the idea is following. Okay, the spin scatter is, instead of doing this, what you're doing is the following. Okay, let me have another page to make it look easier. Okay, what you're doing is following. Okay, suppose your data looks like this. This is your data, suppose, right? I don't know how it looks like, but this is our data. Okay, get the data point. Bin scatter plot means that you would tell me how many groups or how you want to divide this X into how many groups. Okay, this is something you have to decide. Okay, you have to tell me what the group is. And of course, you want your model grouping should not be too sensitive to your grouping method, right? But at the end of the day, you will tell me that this is X, this is Y, right? You decide, okay? You try to group this into one group. You group this other group, okay? And you group this to the other group, okay? Suppose you divide them into 4 different groups. So what is your model here will be very simple, okay? Your model will simply saying that, okay, this is the first group, okay? My model will tell me that if you give me this value of X, my prediction will be, maybe I use the color, right? My prediction will be like here, okay? Why? Because these are the average value of Y given X, okay? I write the model here, right? My model set is I reduce this to one number, okay? Of course, there are many number here, but I reduce the dimension to 1, okay? But one I extend it to the whole line, okay? So there's the reduction and extension idea, right? And then the same here, I would just do the same here, okay? This is my model, right? If you give me this X value, this is my prediction, okay? If you give me X this value, prediction is here, right? Because this average value between here, right? My average value is here, right? So in this is my model, okay? So it's very like bin scatter, right? It's like I group them, I put a point here, but now instead of just a point, I say all this value is exactly here. This is my model, okay? And this model assume I don't need to make assumption on how X and Y are related because we don't have at the end, right? But at the end, it's just like this is my model. It's the simplest model you can get, right? We'll do a Python code afterward, but this is the most simple model you can do, right? And right? Probably some of you actually know when undergrad, I actually do actual science. And if you look at, say, how accident happen or how your people life, right? How long they live, right? And you don't have a nice model, and usually you will see in insurance company, they predict how long you live is based on the data. Data driven is based on this kind of method. Okay, one of the way they do is they come up with a life table, right? Calculating your premium, how long you live, and then calculate how much they charge you, because it's very difficult to have a model how long people live, right? It's to be data driven. Same as you can make your IT manager, right? There's very difficult to come up with a model that how long they spend in your website depend on how the feature you impose in the model, right? In that case, this would be the best way to model your data, X and Y, okay? And you can easily see that although we don't do it, if you extend Y and X into many, many dimensions, you can do the same, right? Because suppose the data is like 2 dimensions, okay? Imagine the case Y is in this vertical dimension, okay? There is this dimension called X, this dimension called Z, right? And you can basically cut this whole thing into many, many small squares, right? Each square, you can calculate the mean of Y, then you can come up with a model, same. So no matter how many dimensions, you can use this, okay? So this is the easiest model, especially if you have a large number of data, this will be the most useful thing, right? Because you don't have to assume that it has to be linear, right? Because the data can tell you that there can be many different weird shape would go on, right? This would be the easiest thing to do, okay? So, so this is the first model we have. It's called the bin scatter, okay? I hope that is clear what we are doing right now, okay? And later we will do our Python code, so don't worry about that. But for the moment, I will convince you that this is the first method, okay? So to make sure that we understand, okay, let's do this example before we do the break, okay? That will make us to understand how to actually write the model, right? Because you have to do it, right? Because for your next assignment, you're asked to do something similar, okay? Want to remind you that in assignment 1, you may find it, my instruction is very detailed, but in assignment 2, there will be less instruction, right? That will, because increasingly, I don't hold your hand for too long, right? I mean, with less instruction, and then assignment 3, I think hopefully the last one, that will be the least detail, right? You will do the rest. I mean, the project is you do everything by yourself, right? So, but let's look at this example. I think we know very well how to. With the background of this is like this is a price information from a hotel price comparison website. We focus on hotel price in a city in Europe, and then this focus on the price below 600. So how we do the model, right? Because we want to look at the case where with the distance and predict the price, okay? So that is the model. We try to explain that. And we will do 2 bins, which we divide data into close or far. And the textbook they use is 2 miles is a cutoff, okay? And you probably ask me how we think about 2 miles. Doesn't really matter as long as you think that fit the best. And this is variable, you can decide what the number is, okay? And of course, you can increase to more bins, okay? And the question probably you would ask in your head is, how do I decide how many bins, okay? And the easiest answer is no one knows. I mean, of course, there's some way you can decide, right? But for practice, for a purpose, is you should think that it shouldn't be really matter how you divide the data, right? You should expect when you do prediction, then should not be too sensitive to that, okay? And it depends on how many data you have, right? The more data you have, the bin you have more bins. You have the less data, you have less bin, right? So I think that would be the easiest thing to say. But There are many things to go if you want to find optimal means, but that would be out of scope for our class. Okay, but at least we tell you how to work on that. Okay, and just don't worry. Usually, if you work on that, you just follow the standard procedure to do it. Later, we will show you the one way to do it is we compare how, remember the regression, how we evaluate the vertical distance, right? So one way to think how many beans you have, okay, is to look at, let me go back to this one, is look at this vertical distance. Okay, is how sum of this vertical distance, okay, will be how accurate your model is, right? Of course, the smaller the better, right? But of course, there's a trade-off, right? Because if you do more beans, then of course, if you do everything has its own bean, then of course, there's no error, right? So the trade-off of how many beans you have and how accuracy you have. So there's two trade-off, right? So there's a punishment for more distance, okay? Then you want to get more beans, but there will be punishment for having many beans, okay? And you can try to, I say, IT manager, you will try to figure out, right, which the combination, which one to fit your objectives, okay? There are many ways you can evaluate that, but you can see the height and the thing that it can be done. But we talk about some called AIC, BIC, those kind of stuff. But I mean, in the moment, we just keep this. I mean, there are many measurements you can look at, but at the moment, we just don't worry about this part. Just given this procedure, that's fine. Okay. So let's try to work out again. I guess you don't need me to explain why we need this slide, right? It's very clear that we have done this many times, right? We have a NumPy and pandas package and download the data from using Panda idea. Okay. And let's, okay. And this is the thing. And let me load it, and then, okay. Once you load this, then probably you want to look at the data, whether this is what we want, and then you do the head, right? That's a standard technique that we'll be using. It just wait a little bit, I think. When it starts, it takes some time. And then this is the data we have. I think that's not something too much worry about it. But at the end, remember, we look at the price, okay? And look at the distance from the city center. That will be the thing that we want to understand. This is the Y. Okay. And let's go back to the slide, okay? The next thing is data filter, okay? And I think if you do the assignment, then you will notice this is a rather standard way to do it. Okay, just using the LOC method, okay? And let me copy this guy. And place it. Okay. And I think that's I think you know this very well why we do that. Let me quickly go to the next one. Okay, I think that's more fun. So the first thing we do is to divide them into two categories. Okay, the way we do is mp.where, right? And trying to see if less than 2 miles and it's close, otherwise far away. And then we declare to be categorical variable, okay? Because we need to plot them. So that would be the idea. That's called PD categorical. And category is what are the all possible values there. There's a set function here. And I sort them, okay? So that would be something that we know very well already. But in case you forget, then you can copy that code. Okay, this is the code. Oh, sorry. There's a, okay. So that is done for the purpose, okay? We have defined the category based on that, okay? So you will be, later you will see if you divide it in 4 groups, then you just do it 3 times, right? Your 2 groups just say less than 2 or more than 2, okay? So that is very simple. Is that okay? Up to here. Now we quickly go to the next slide, okay? And we create a data frame that try to calculate average. Remember, we divided into two groups, right? And you look at the group based on X, you calculate average of Y. So that's why we group by the categorical variable distance to, and call expected price in two categories, and using the mean to calculate the price, okay? And we'll reset the index, okay? Okay. So let's run this particular code here, okay? And I hope this should not be something difficult for you to remember. Okay, so this is the code. Okay, now we already have this data, right? Now what? Oh, that's okay. What next is we try to plot the bin scatter plot there. That would be something we do, right? This is a matplotlib and X and Y and plot the scatter plot, and that's our model, right? And the model like this is something that we have done, but this graphically, this is the model. Okay. Okay. And this is the first model there, okay? And here you will see I have far and close reverse. So if you want to make sure that you want the way that close to far, then you just change this reverse to false, and then you do everything that will it will reverse in this way. So it depends on whether you want close to far or far to close. You change in this form. Okay. So now I think what I want to show more before the break is, I think there's nothing new. I mean, they're similar to what we have done for the data, but we want a little bit further. Okay, we want to give the model, right? Because that is just a scatter plot, right? Because you don't give the model. Okay, so what we're going to do is going to give you a visualization of the data. Okay, at the end we will give you this guy. Okay, we'll say, okay, put a number there. Okay, okay. The idea is, this model, how it's being used is, you give me the distance to the city center, and I ask you whether it's 2 miles more or 2 miles less. If more than 2 miles, your prediction is 91. 2 miles less is 115. Okay, and I want to plot this number to the plot, right? Because I want the model, right? Because without the number, that's not very useful, right? It is already your model, right? It's whether 2 miles or not 2 miles. So the way we do, probably you already learned it, we will actually use the matplotlib access idea, okay? Instead of the standard thing, we use the subplots idea, okay? So which is slightly little bit more complicated, but in fact, this is usually the way that you look at the Python code. This is more standard. Okay, the one I do is a little bit shortcut. But the way we do is, we have a subplot actually give us two different objects, okay? And we would separate them by figure and axis, okay? And the axis would give us the scatter plot, okay? And what we do here is to, for each number, okay, each step point, we try to attach the number to it, okay? How to understand this is, I have for loop, okay? And for every counter of xi and yi, zip over x and y, because why the zip is because I have x and y, and I want to pair the first element from x and first element y, right? I want to put the number there. So what I'm doing is, okay, the zip is the following. So suppose x, right, is say 1, 2, 3, 4, right? And say y is like 3, 4, 5, 6, right? But we actually don't want this guy, right? Because what we want is we actually want the following. We want 1, 3 is the data, right? And 2, 4, right? And 3, 5, and so on, right? Say a thing there, right? And that is called zip. XY is a list, okay? Where this is the first element, second, and the third and fourth, right? You combine them element by element, you call it zip. So I zip them together, right? The first element will be this first data point, okay? So that means that I look at this here, okay? And I put a number there, okay? And first thing I run the number in case this is not, it's integer, right? I want to put an integer. I put a string means str means that I change it to string to put in the table. And where I put it is exactly the coordinate, right? But the coordinate is a point there, so I need to move a little bit. So what I do is coordinate is the data, and XY test is I move a little bit up, 4, 4, so on the right upper corner, okay? And that's test coordinate offset. So that what we do is this code there, and this other thing are the normal, okay? So let me quickly copy the code, and then you will see what's going on in the table, okay? Hopefully this will give us what we want, okay? So let me combine them and run once and for all, because I guess there's no need to separate them. Okay. Yeah, I can erase the cookie. Okay. Then I run this guy to give us what we want. Okay. So this is the code. Okay. I hope it's clear that what we're doing, right? Because we already provide you a model, okay, that gives you 2 groups. Other break we will talk about 4 groups. And some of you may think this is simple and very easy indeed. Okay. If you remember the diagram here, right? We divide this into the different groups, right? And later when we learn one of the machine learning method, okay, is to ask the machine to tell us that ask the machine means there's some way, a smart way to divide them into different groups, okay, in a form of tree, okay? It's like you build what we call the classification tree or regression tree. You will tell me that, okay, based on data, ask me questions sequentially. First, ask me x is bigger than or less than certain number, and group them into different parts. So it's a nonlinear prediction. Okay. So, but maybe say need not be a continuous group. Okay. Maybe this is the same group. What I mean is, say it can be the first and the third actually the same group. They allow that happen nonlinear. So maybe you average this and average this, give just another line. Is that clear what I'm saying? So here, the 1 and the 3 can be in the same group if you allow the regression tree. But that will be something we learn later. Okay. For the moment, we learn the simple one is different group are unrelated, but it can be the case this 1 and the third may be related, and how you cut is based on the data. So, and currently the grouping is we decide what the grouping is. Okay, there's no systematic way to decide the grouping. Okay, and there's no relationship between grouping. But the machine learning method we learn later, you see, they will from the data tell us that how you cut this, and there may be relation between groups. Okay, but that would be something more advanced. Okay. So I guess now I think it's time to have a break here. Because after that we'll do 4 groups. Then this is the end of the first method. Okay, this is a bean scatter method, and And then we will learn another method we call later we will see. And the second method we study, okay, is called the Lewis, which is trying to give you the nonlinear line. Okay, but we'll do it after the break. Okay, so I guess it's good time to a break of 15 minutes. Let's resume at 3. I guess 3:43. Okay, and we can fill in the form, and I'll try to answer any question you might have during the break. Okay, take a rest of 15 minutes. So let's see the your response and see if I miss anything or you have something to say. Yeah, today's Saturday. True. Can we finish class early? Yeah, we try to. We try to do it faster so that you can go home earlier. I know. I mean, I living far away, Hong Kong Island. So of course, I want we are your interests are aligned, but we have to finish things, right? So um, yeah, you can do remote, no problem. Because you reply trying to let you tell me that uh, what you don't know or what you want me to talk more or less or faster, slower, because I adjust accordingly, right? Say now you want me to faster. Okay, I say I try to go faster. Okay. And if I want to go faster, then I will not run the code, some of the code in the class. So you have to run it uh, during the break time or I skip some of the code. So that is a very good question because today is Saturday, right? And I ask you which day, then I try to see what answer you give, right? Apparently, people who give Wednesday or Monday is the closest. This is good, right? Then what surprised me is someone writing Wednesday, but I don't get why it's Wednesday. But anyway, someone writing Wednesday completely. So the question would be which data you use. If you're IT manager, so if you see that, what happened, right? And probably you would drop this data point, right? And these two are pretty good, right? And this one you can explain, right? Because we're a Friday class, right? So putting a Friday is the best solution you can get. Uh, yeah, I think it's okay. We get the right answer there. So it's bin scatter plot. Yes, yes, that's a good one. Yeah, Q there's no answer. That's the right thing. So overall, it's okay. Not too slow, not too fast. Maybe I can go slightly faster because many of you require. I don't read Japanese, but I think it means very tired, right? Yeah, today's crowded. What's this? Something I should know? Or what? What's this? What's that? No, I don't know what's that mean, but is it something Important, I should know. No. How to spell that? Leroy J. Oh, what's this? Card game, okay. Fine. No, nope. Okay. So let's quickly, as I said, you want to go home earlier, so I just quickly go over this one without because it's similar. I'm not going to copy it. You can do it on your own. So to save time. So if you divide them in 4 groups, okay, then we'll do 0 to 1, 1 to 2, 2 to 3, and then 3 up and more. And there's some issue when you plot, right? Because 0 and 1 you can plot at 0.5, 1 and 2 you plot at 1.5, but more than 3 where you plot. So the book suggests you do the following. The minimum is 3, right? And you look at data, the maximum of the distance is around 6.8 or 6.9. So run up to 4, so run to 7. Then you put in the middle 5, right? Because you need to put the data there, right? So how to do the code? As I said, I'm not going to run it because you want to go home earlier. So you can run this by yourself, okay? Or you can check the other parallel class section. We have the code already. So I just skip there, but you can check the result. So I'm not, but I'm going to go over the code without running, but I just dry run with you. So what we do is we create distance 4, look at using mp.where, and see if less than 1 I put 0. Sorry, 0 less than 1 I put 0.5, which is the middle between 0 to 1. And otherwise I put np na, right? And after that I do another thing, and then said if it's between 1 and 2, I put 1.5 because this is the middle, right? And otherwise I input whatever is there, right? And then go on between 2 and 3, I put 2.5. And then bigger than 3, I put 5. So this is the thing that is there, okay? And to save time, that I mean, I run it during the break, okay? I would do it next break. I would run it, and then you can still see it. But in the moment, I just skip this part. The categorical is also the same, okay? You can say the categorical that, then you do the summary, right? And then you can plot with this one, and then you will be the graph like this, okay? And this is the model, okay? And now you have this, then probably you want to tell, right? If 0 to 1, my model tell me is 133, 1 to 2 is 99, 2 to 3 is 98, and 3 to 7 then will be 84, right? So that is my model. And the thing you want to present is you want to plot the original scatter plot, then it will tell us the model more explicitly. So that's how you present your data in a nicer form, okay? What we do is use the subplot again, okay? And what we do is do the labeling, and I will set the limit, okay? Which means that the y-axis is from 0 to 400, okay? You don't have to do that, but the graph looks better if you limit the y from 0 to 400, okay? And what I'm doing is because I want the original scatter plot, because at the end I want the outcome like this, okay? I want to plot this line, the dots, and also line, because the line gives us the model, all right? Because this is actually here, if you have the red dot here in the middle, will be the bin scatter plot, right? But now we change the bin scatter plot to this model, okay? So how do we do this is we have to use the idea of zip again, okay? And here is the data, A and B is the interval. We cut the bins, okay? 0 to 1, first bin. 1 to 2, second bin. 2, 3, third bin. 3, 7, last bin, okay? While you get 7, the maximum distance you can check is 6.8. then I put the 7. Okay, you can do NP dot max x, then this gives you 6 point something. Then this is how I get the 7. And what's h? X is, I draw the line, there's the height, right? H is the height, which actually the data from the bin scatter plot. Okay, what I'm gonna do is I use the for function x dot xn, the y value, I ship them together, and then I add a line where it start, where it end, the distance, right? Because the plot of this is a line, okay, to tell me what's x, what's the y, right? Because you plot a linear line, you need 2 points, right? So this start value, end value of x, start value of y, end value of y. But since I horizontal line, it's the same. Actually come from h, right? H is the y value, right? A and B x value. So you can plot that, then you can get this one. Is that okay? I will copy this code when I do the break, so you can see how it being work. But I save the time in the class. I mean, we do it here. Okay, I'll do it. But this is the model, right? So you can see it's a pretty good model here because it can tell me that, okay, you tell me what distance, what's my prediction. Okay, so that will be the model I have. Is that okay? So now we have a very nice model. Okay, and the only drawback, this model is linear, right? And the problem is it's kind of discontinuous, right? You look at this model, one of the drawback is when you are 1, okay, or close to 1, it can be like 100, right? And you slightly less than 1, you become 130, 40, right? So suddenly there's a big jump. It's not very desirable, right? Suppose you are for 99 miles, what numbers to look at, right? You should look at this one or that one. It's not continuous, okay? So the first thing we want to do is to make it continuous, right? To draw a smooth curve, right? So there are many ways to do the smooth curve, and the textbook they do is to a methodology called Lewis, and the thing is like try to plot some polynomial, then it's very smooth, okay? And we are not going to cover how to do it, right? Because we'll make a black box. There's some way to do it, okay? And Python tell the answer, okay? It's like we don't have to know every single thing, right? But the model looks like, okay? It's black box, okay? Just like later we learn machine learning method, we just tell you that what it does without telling you all the algorithm, how it being achieved. Because you will learn that in another class if you do machine learning, okay? So I'm not going to repeat what you will learn in the next class, right? Because so how do you do that? Let's do it, right? This one we'll do, I'll copy that. So what I'm doing is I will use a important package called stat models, or statistic model. And through the API, you will import as SM, statistical model, okay? And what I do is I would do a non-parametric method, Lewis, and X and Y, and fraction 0.6 with somewhat a smoothing parameter here. You can change up and down, depending how smooth you want, but 0.6 I think is default number, okay? Usually you don't have to worry about that number, just keep there. If you don't like that, you can change up and down, that's not a big deal, okay? Once you did that, you give me the smooth X and smooth Y, and that's, you can use it for plotting, okay? And what I do is I put, later I will do is I have scatter plot, this all the data, and I plot the line, right? And I just call label, and I will give you this one. Let's do this one because I think this one is something that we should demonstrate it to you. Because otherwise, and also I want you to do it as well with me, okay? So just copy the code here, 2 lines there, and then just try to do that. Okay, so this is the code that we copy from that, okay? And now we are going to copy this guy and just place it. Okay. There's nothing very deep here. Okay. Just run. Okay. Take some time, a little bit time. Okay. This is the model like this. Okay. And as I said, if you want to change this number, you give you another line. Okay. It will be less smooth, right? It's more normal, right? More straight line. And then if you go to say 0.2, you'll be more curved. Okay. The fraction means how much data you try to smooth out every time. Just a local thing. The smaller the number, then it allow the local feature being used more. So you can use 0.3, 0.5, whatever you like, right? Depends on how much data you have, and the default is 0.6. And there's no hard and fast rule which is better. But at least look at this diagram. It will tell you that how nonlinear the things is. Okay. And I don't know whether you like this one or you like the 0.5 one. It's really up to you how curve you want. Okay. You may use 0.9, 0.8, 0.7. This is your choice, right? It's every time that you look at how much data you try to plot, right? Okay. Is that okay? I mean, as I said, this is a black box. No, I'm not going to talk about those. If you really want to go into detail why the case is true, then it is usually the step probably you must do a step master to understand what's going on. Okay, we'll just skip it because the purpose of running this is to telling you that to idea how much bin you want to. Right? For example, you just look at this is maybe this can be 1 bin and you cut more bin here. So this is a usually is not used directly. I mean, you can use directly, but very often you would try to give you idea how you cut your bins, right? So that would be a more informative choice, right? So I hope that would be a good, okay? Is that okay what we're doing? So we learn 2 different methods. One is you cut X into different groups and then calculate the average of Y there. That would be your model. The next one is like I have a black box tools but this is nice because it's continuous. Okay, I can plot them. You can see how you predict, right? Whether you like it or not, I don't know because this one say the further away it goes up, right? So may not be very ideal, right? For this one, I don't really like this one because it doesn't seem to make sense here. I mean, at least from my knowledge, it doesn't seem to be the further away is slightly more expensive. It doesn't seem to be right, right? Maybe this due to this data point here. So if you take away this data point, then it will be more normal. So then the question go back to your data. This will tell us whether you have to take out some data outlier, right? Probably you read the news. People said now ChatGPT 4 is getting stupid. I mean, there's a news today. Okay, I mean, you read the article said why? Because people start to talk to the AI try to learn, and some people are not very smart enough compared to the data set. So the more interact with the ChatGPT, then they learn something stupid, because maybe some crazy people try to feed something stupid to the machine, right? The machine becomes dumb, right? So same idea here. The question is whether you should take this data point away from the model, right? Or you think this is not enough data here, you just stop the model from up to here, this will be a nice model, right? So that is a question. But anyway, as we said, garbage in, garbage out, right? In the class 1. So whether you keep this is a garbage or not, you decide, right? Hard to say, but I would not take it too seriously because there's not too much data here. So if you ask me, what I do is I would just actually cut the data beyond 5 miles, right? Which you know how to do, right? The FLOC cut it more than you make the data more condensed on the data you know, right? So that would be what I do. Is that okay? we learn two methods. Okay, is that okay? If okay, then we learn the most important method. Okay, besides machine learning is the regression. Okay, quickly. I guess most of you have learned it in the undergrad, so I will try to be as quick as possible. Okay, but in the case that you think I'm too fast, slow me down because, well, it's easy to go very fast for me because I taught this too many times, regression. So this is again, as we see, we have a slope intercept form, right? This alpha slope, beta is the intercept. That's how we interpret, right? So that's what we mean by alpha is x equals 0 is y, and beta is if you increase for any x0, you increase by 1, how much y you increase. Okay, that's the slope. As we argue already, how to find the best alpha and beta is the line that minimizes the distance square. So if you look at this diagram again, okay, now this is not the, it will be this here, right? The idea is like minimize distance, then you can look at another line, right? Suppose I have another line which is color of, I don't know, light blue, right? You look at this line, right? And you look at the distance again and see which one give you the least sum of the square distance. That will be the line that you try to fit, right? So that would be the idea, right? Just you try to find different lines, right? Try to see how it varies, okay? And this explains y square, but I think you learn it in the undergrad anyway. In case you don't know, just ask me. I'm not going to go line by line, but look at the graph. This is my undergraduate slide. So you can see the distance of the blue and this one the red. You square all the distance, sum of it. That will be the criteria that we're doing. So that's why it's called least square is a less sum of the square. And if you learn calculus, well, way different, right? Then you know how to derive that. Okay. Actually, it's not difficult to prove. Okay, but we're not math class, so we don't talk about how to prove it. But the idea is the beta is a function that is a fraction covariance over variance. Okay, and I don't want to explain why this is true, but rather I will point you to why it is true, right? Without doing the proof. And one thing you do notice that the beta is related to covariance, which you learn that is measuring how x and y are related, right? And the reason why you have to divide by variance because the size of x can change, right, accordingly. So that's why you normalize it, okay? And the next part is the intercept. Shows you that if we write this formula quickly, you will give you the form that y bar is equal to alpha hat plus beta hat x bar, right? And immediately from your math knowledge, the line would pass through x bar, y bar. Okay, so that is important because regression actually tells you that the best line must pass through the center of the data. Okay, so that's a one important property. Shouldn't miss, and this is only true for regression. If you look at other machine learning method, this usually is not true. Okay, so but I think this is very important. Is important property, right? Because if the line doesn't pass through the data center, then doesn't seem to be a good model. But machine learning model usually don't satisfy this one. Okay. And that's what he said, right? It's passing through. The blue is where you look at all the x to the center and y is all the center. This point will be passed through by our regression line. Okay. Now, the next thing we want to say is now we know how to estimate. Okay. Of course, you would not need to worry about it because Python automatically gives you all the answer, right? So you don't need to worry about the formula, which I'm not going to ask you anyway. But the first thing to do is we predict something, machine gives you something, right? You always, your IT manager, you click something comes out, right? The next thing is, okay, something comes out, we need to make sense of it, right? It's a good thing, okay? So what we're trying to show you is how to evaluate how good the model is, right? Because so far we didn't talk about how to evaluate, right? We told you that's a way to estimate the model. Is it good or bad? Okay. How to look at good or bad is the following. So it's look at the residual, okay? Is look at because we are minimizing the vertical distance, okay? And later we will show you that this residual, which means the distance, okay, which means that someone want to minimize this guy, okay, this guy is very important to evaluate the performance of a model, okay, and we will look at this number, which is called SSE later, and we will divide this by number of observation, and this is our measure of fit. Later you will see this number is, we will compare this to other machine learning method based on this number. Okay, it's how fit our model is. Right, later you will see, but that is the sum of square residual and or average square the residual. This is the thing we want to do. In the regression, turn out to be very nice. This is 0. In other model, need not be, but in this is very good behavior. Okay. So what I want to look at is we want to run the regression, right? We want to look at how to do it in Python. Okay, I think you learned it in undergraduate, maybe you use Excel or your other method. So what I want to do is to do a Python. Okay, Python later will show you that the intercept is 133, the slope is 14. Okay, and how we interpret this is important. Is what does that mean? It means that if you have intercept of 133, means that the hotel is city center is 133, and negative 40 means that for every mile away, or km, I forgot, mile away, then you will have $14 less, right? That is the line like this, right? So let's run this regression, okay? To run the regression is, again, we'll use the stat model API, okay? Which have seen that SM is can run the lowest, right? The same package there. Okay, there's many packages there. You can look at the menu. There's so many packages, but we only cover the thing we need. There's a regression. Okay, we put the way we do is more like the matrix algebra, okay, or 矩阵这个线性代数. Okay, if you learn that. Okay, the way we do is we define x and y. Okay, and we need to add a constant to it. Okay, that become a big X, the matrix X, and we run a regression based on Y and X. Okay, so that is the way we run. And later you will learn that this is not the only way. We can run it as a formula. Okay, and probably ask why we run this way. This is more like statistician way to run it. Later you will see we will not use this in the way that we do, but let's do this one because easier. So we'll call sm.ors, basically run the regression. Okay, and we define the model and we fit it. Okay, and I print the summary. Okay, so let me do this because it's so important that we have to do it together. Without doing it, all right, we can't sleep well because this is the single most important thing we should learn in this class, right? If you are sleeping, you're sleepy, please wake up. It's time to wake up to run the regression. Okay, if you're not waking up, you're sleeping right now, that you lose the most important thing in our class, right? Is run this regression. All right, let's run this. And the important point is, okay, if you have your model, you just change this guy, right? So all the rest will be same except the first 2 lines, right? If you have your own regression model, okay? So the most important is look at how to interpret your Python output, right? And I think last year, this is what I asked in the exam, all right? I just give you this output, and I ask a bunch of questions, you how to answer it. Okay, so very likely that I will ask a similar question in the exam, because this is something I want you to know, right? I give you this output, I need you to tell me how to do, right? You tell me what is your conclusion and what is your prediction, right? So in this particular model, what we have is run this regression, and this the important point is this middle thing is the most important. That is the main result. Okay, so let's go slowly before we go to the break. But this is the thing that we need to care. Okay, and for the class before we have dinner, that is the most important thing. Okay, this we'll cover after the dinner. Okay, next class. Okay, this coefficient, and this give me the alpha, this give me the beta, right? Constant means the coefficient is a slope, sorry, it is an intercept, right? And distance is slope. Okay, so it's actually the model, right? If you try to draw this, which we will do in Python, but what you do is this distance, right? This, and this is the price, right? What it said is when distance is 0, this is 132, right? And for every mile away, 0 up to 1, you drop by 14, right? So something like 14 means 8, 118, right? And so on and so forth, right? In draw on. Okay. So this is a model, right? You collapse the many complicated set, right, to a line, to a line, right, which represent by these two number. Okay. And after our dinner, we'll make sense of all other things. Okay. This is we will focus on this one, this two, and later very soon we'll talk about this guy, R square. But I can tell you what is it right now before the break. Okay, what's R square is a way to measure how fit the regression is. And if you recall, this is 15% of the data. The variation of the price is explained by distance. Okay, so what it said is it has 15% explanation power, if you want to put it loosely speaking. Okay, so of course, this number R square is between 0 to 1. Okay, if 0, that means the model is rubbish. 1, the model is excellent, perfect, right? 15 is okay, okay, not too good, not too bad, but R square is something you want to look at, right? And so far we didn't talk about more, but after that we'll talk about more stuff. But these are the two things that we'll cover up to now. Okay, so we'll give you more definition of this after the break. Don't worry about it, because these are the things that we try to cover. Okay, so for the moment, let's have a break of 15 minutes. We come back at 4:30. Okay, so I think we have enough material. As I said, if you want to leave some comment, I mean, I think it's good time to do it. So maybe another break for you. So I said this one. Okay, in case you want to leave any comment, but I guess if you want to leave, otherwise you can just take a rest. Time you can do the scatter plot for data point, which I skip. You can try to do it in the break. 张老师的share一下吗？本科的时候我们有做过一些把好东西 share 给大家。对，问你有什么 share 的 share？你比如说有什么好记的？把这个 video 放上去，我给大家放一下，大家有没有什么困扰？对啊，我当时我不来让记录发。哦。天天出去吃饭。对，发一下我。那个多巴胺。那这个外带的话，大家看不清。这个每个人自己做的，一些外带没有说会看清楚。多点东西了。各种各样的地方，大家一起。比较好。Hi, good to be back. So let's quickly continue. Okay. Okay. Let's see if some question or anything is going to be shared. Oh, where we are. I think we'll go to the report. I think multi-item, yeah. So far, no one have any answer. Linear regression, yes. The speed is okay, so I think I'm not too fast, although I think I'm faster than. Oh, means 同志们辛苦了。OK， 明白。I think that we have a very good Japanese here. Okay, good. So now we have look at the result, right? So it's good to plot it because you want to show how the data compare to your model. Quickly, I will draw this one, but I guess I don't need to explain this guy. Oh, I do have one code to explain here. Is we want to plot a line, right? So the thing to do is what we call the result you regret. Dot predict means that you make a prediction. And remember, dot predict is the model. You feed in what x there, you give you what the y is. Okay. So this is the model we have. Okay. Oh. So there's a question asked here, but I can't see the picture. I don't know. I can't see it. Let me solve this later. Where are we? Yeah. Let's plot this guy. Oh, I think okay. So you will see this line, right? Basically, you reduce all the blue thing into the red one. Okay. Use your data from the blue. Okay. Reduce it to simple blue one, and this is your prediction model, right? So that would be the model we have seen, right? So that the red thing is our model. So whether you like this one, or you like this one, or the one that we just skip, right? I don't know. We will later we'll decide which one is better. But at the moment, we just tell you this model. Later, we'll teach you some way to measure it. Okay. Before the break, I mentioned one particular way that you can look at how good a regression is what we call R square. Okay. And how do we define this? It's very simple. So first, the thing is called SST. Okay. But I think instead of looking at the formula, I think it's easier to look at this graph. Okay. In this graph, okay, the green dots are the original data. Okay, X and Y, which we know very well, and the Y bar is the blue as a black dashed line. And what's this one? Y bar is the model that has no model. What I mean is, if you don't have anything, right? The bin scatter plot, only one bin, is no model, right? The thing that this is your model is a Y bar, right? That's a prediction, right? Without using anything. Y bar is the bare bone model, that's no model, right? So whatever you do, you would compare to this benchmark, right? Because what you try to explain is the blue one, SST, is the data point to the mean, right? Because without anything, the best thing you predict is Y bar. So what you want is to say why your answer different from the Y bar is because the X value, right? So SST, which is sum of the distance square of that, right? Because the blue one would be something like this, right? This or the distance like this add up, right? This SST, right? Okay. All this distance, the line, or the distance you square sum of it is called SST. It's the total thing you want to explain. That's why the square sum of square total, SST. Okay. And you can easily see that the model successfully explained is the deep red one. These are the part that explained by the model. Okay, these are the model explanation. Okay, model type. This is the thing. Okay, the square sum of this red one is called the SSR. Is that okay? This is the part explained. So R square is defined as very simple. R square is simply, as you see the slide, right? Is this SSR over SST, right? Is that the total you want to explain is explained by SSR, okay? And that is how good the fit is, right? How good the fit regression is. The bigger, the better, right? You can easily see that if it is 1, that means that your line is perfect, right? If it is 0, that means that you're rubbish, right? Is that clear? So that is between 0 and 1, okay? And perhaps not surprising, this big R square, it is same as the correlation coefficient that we learned in chapter 2. This called small r, this R square, same. Okay, this is actually called small r. Okay, so correlation, right? We learned that in the chapter 2, right? The topic 2, right? That R square is exactly the big R square. Okay, and do note that the small r and big R only relevant for single simple regression. Use Y and X. If you use that and many others, then this doesn't hold anymore. Okay, there's something you can have a formula, but this is not we care. But the idea of R square still hold, right? If you have many things, it says 3 dimension, it's still that the plane you just explain the ratio that explained by the regression. Same idea. Still the percentage that the fit is going to be. Okay? Still 1 is the best fit, 0 is the worst fit, right? That is the idea. Okay. So one interesting thing I want to mention for the regression, only for regression case, is the SST is SSR plus SSE. Okay, and you do remind you that SSE, you look at this, is this one, right? And this SSE is indeed when you run regression, we're trying to find the slope of intercept to make this as small as possible, right? If you remember that, right? That is what we're doing, right? We find the slope, intercept, try to make SSE the smallest, right? If you still recall that, okay? And if you divide the SSE by n minus 1, okay, or n minus 2, in fact, in this case, it's called MSE, mean square error, which is up here in your slide after the next one. Next slide with there. And MSE, that's the average, because the more data point you have more this, right? But this MSE, later you will see, is we use it as a benchmark to compare across different models. Okay, if you compare a model with machine learning, compare the model with bin scatter plot, whatever thing you want to do the MSE, or sometimes you will do the RMSE, which means that you take a square root of that. Okay, these are the benchmark you compare across model. This horse racing, right? How you compare different models, how you compare. But this always you can compare, right? Because your original data, your feet, the distance, square, easiest, no matter what model, you can use this comparison. Okay? Is that okay for this one? Okay. So R square we explained already. Okay. And as I said, this MSE or the RMSE is the way to compare across different type model. Okay. Of course, you can compare different regression, but of course, you can also compare different method you're doing. Okay. And the machine learning later, you learn that this is how you do the horse racing. Okay. And that is, remember, regression is actually here, right? It's R squared here. And if we have time, we will tell you that these last three, also the horse racing, log likelihood, AIC, and BIC, also a horse racing criteria. Okay, but we will delay that until we go to that chapter. So far, the regression, we use R squared. Okay, and you may ask how to calculate MSE. RMS is not here, but we will derive that. Don't worry. Okay. So let's go to the slide. Okay. The thing is how we can calculate that. Okay. Now, this slide that we can calculate by scratch. Okay, but I just show you because we don't use it, but I just show you how to do it. The first one, calculate using the mean, right? And you calculate sum of this minus this square, right? This is SST. You take a projection minus y bar square, give you SSR. SSE will be this minus this square, right? So this is the same formula. Remember, double star is raised to the power 2. Okay, so R squared like this. We don't use this one. I just show you that the formula is right. Okay, what we use is this guy, very simple. R result to R squared. So this is what we do. Okay, because I guess this answer is here, 15%, right? Same as the one in here. Okay. I guess the more important part is to calculate this RMSE, right? Because that is the thing that we care more. That's the reason why we need SSE. Okay. And later you will learn that you will need this guy, right? So to calculate SSE. Okay. And at the moment we use this function. And later, if you have reload the machine learning package, you can have a function directly do this one, but behind this guy. Okay, so this SSE there. So what we need is to R square, we have to do this one, right? Adding up each element, you take the y and minus prediction, right? This square, right? And then we need this, the rest, right? And length means that look at how many y, how long it is, right? It's the list, right? How long the list, and you minus n minus 2, and then y2 here, because we have we estimate two things, intercept and the slope, so minus 2. So later you will see when we have more variable, then you minus more. Okay. So that means that if you have more variables, later you will see this one is smaller, but when you divide a smaller number, this one bigger. So that's a natural trade-off of the two. But anyway, maybe you need to print. Okay. So this will be the one that we look at, 38.x. Okay. And later when we learn different model, we will compare this number to the other. Of course, the smaller the better. Okay. Or you can pin MSE, the two numbers will be same, right? Either you compare MSE or RMSE with the same idea. Some of the reason why we want to take RMSE, because you take a square root, then it's smaller number, then easy to compare, much faster. Because when you have large number of data, there will be billions of stuff that will be less is comparable, less in the better scale, right? Is that okay? Is that okay for this one? So we later we learn horse racing will be based on this criteria. Okay. Is that okay? Is it too fast? Okay. And I'm not covering this one, but later you will see there's a package we will run, we rely on later. It's called sklearn. It's a machine learning package, and we have using linear regression. They do something similar, but you can see the code is rather clumsy there. But I'm not going to cover that at the moment. Later, when we use a machine learning model, we may use it. But in case you're interested, when you look at Ask AI, they give you where we say to run regression. I better tell you this is one way to do it. Okay, and you can see this is the way I mentioned. Okay, if you give me this learning metrics, then you tell me that this function give you what we want. Okay, but later we'll use this kind of method to calculate the MSE, RMSE as a comparison. Okay, is that okay so far? Any question? So I just go quickly to remind you what we have been doing. First is we have a method called the bin scatter, right? Which you have seen it, the graphical method, but now more than the point, we extend it to the range, right? This interval, this interval, this interval. The average of value of y will be your prediction model. Okay. The second is the nonlinear smoothing. That the Lewis, we have learned the Python code to run it. The third one is we learn how to run regression. Okay. And we learn how to use the stat model to run this regression, and how to interpret the coefficient, how the R square there. The rest will be covered after the dinner. Okay. And we know how to plot the diagram. Okay. And then we understand how to evaluate the model based on R square and MSE. Okay. And R square only valid for regression. Okay. And MSE will be universal to any kind of model you can imagine. Okay. So that will be the two things we are going to do. Is that okay? I hope we understand the chapter 7. I just want to iterate that it's a master class, so we can't cover every single thing we want to cover. If you want to have a deeper knowledge, please read the textbook. Okay. Don't expect it's undergraduate class, we cover page by page. It's not going to happen. Okay. If I do that, it's not a 1 year master, not 1 year master class. It's a 3 year master, right? Since we're doing it one year, so you have to do some of the work by yourself. Okay. just like your Java, it's like Java class, right? So now we are going to talk about one thing we call the transformation of the variables. Okay, that is very important because regression linear just go to have a linear line, right? And we've seen that this is linear thing is not the best thing you can do, right? And many times a lot of things is non-linear. Okay, and in this chapter 8 is trying to talk about how to do it in non-linear way, right? We learn one non-linear way, right? It's the bin scatter or the Lewis, right? But we want to do it in regression framework, right? How to do that? That's what we're doing. Okay. And the first thing we do is do transformation. Okay. It's to transform the variable to allow nonlinear relationship. So as you can see, there are 4 different ways. Okay. In our class, we focus on first 3. The last one is very simple. Just you divide the data, then become ratio. But anyway, but we will do the first 3. Okay, the first one, log, is very common. Okay, why? If you remember why you take log in the high school, right? Why you take log? Anyone recall why you take log? No one. Fine. Okay, why you take log? Log is the way to represent growth, right? If you learn the calculus, what's natural log, right? If you forget that, doesn't matter. Put money in the bank. Okay, you put them in the bank, then we learn is what you call simple interest rate or compound interest rate, right? And that's log thing, right? Log is the way that have compound interest rate every single second. The approximation is a log, all right? That is what you learn. But anyway, if you don't remember that, that's fine. Okay, log is something. If I teach in statistics, in our case, is percentage change, 百分变化, right? So it's percentage change. Okay, so don't worry, we will talk about that very soon. So let's see the following model for transformation. So the first one we know, we try to explain y by change of x, right? Just the example we have is like the hotel price change according to change in the distance. Okay, you change distance by 1, the price go down by 14. Fine, that's okay, linear. But if you do this, instead of using x, we take the log of x. What does that mean? It will mean that if the distance changed by 1%, say 1% further away from the center, then the price would change by beta. That is nonlinear, right? Because percentage each you move will be this. Okay, which will give you more give example, then you will see more clear. But this is what it means. Okay, don't worry, we'll give example, and you will see what's going on there. And this one is what? This one is like if you x change by 1, y will change by beta percent. Right? That means that if you are away from the city center by 1 mile, the price will change by beta percent. Okay. Last one, log. Obviously, this means that if x change by 1%, y will change by beta percent. Okay. So don't worry. Basically, log, you just change the percentage change. That's it. Okay. 百分变化. Okay. No, don't worry. We will give example to make it more clear. Okay. So this is a model we have already. I'm not going to copy it because it's already there. We run the regression. The only thing I want to talk about this is because we will introduce another way to run the regression. I think it's more convenient as long as you work in the regression. This is more convenient too. It's called the formula.api instead of API. And then you call statistical model function. Okay. What you do is you don't no longer need the x and y. You run a regression, the OS, and you tell me what's the y here, a snake, and tell me the X, and you tell me the data where you found it. These are the column names, okay? And then you fit it, okay? And you can print a summary, and you can plot here, okay? But this is the model, okay? Let me do it, okay? Let me do it, and then you will see. I think then you don't need to add constant. You can forget many stuff, but okay. So let's run this guy here, okay? And I print the summary, okay? So if you don't want it, you can make, okay, this is the way, okay? So give the same result. See, so this is easier when you just run regression, the formula style, okay? And it's not very convenient when you try to do machine learning or other, later you will see some what we call cost validation or other method is not very convenient. But this is the convenient if you just, I just run regression. I don't care elsewhere, I just do regression. This is the most convenient way, okay? So as you know, your IT manager, right? You accept Python, right? There are many ways to do the same thing. So we have to learn different way to do different thing, right? So just like to make you not hungry, right? You can eat rice, you can eat noodle, right? And then depends on the time, right? When you eat rice, you use chopsticks, right? And spoon. When you eat noodle, you may need the fork, right? I mean spaghetti, right? So on and so forth, right? So that is the rule, okay? Now the next part is to print it, okay? And the only thing that I want to mention now, the prediction, you put it, the good thing is when you predict in this way, you just put in the data and predict, okay? So that make slightly different, okay? So this is how you would, you don't need a constant. So this is how you would do the prediction, and you plot it and everything the same, right? So I think I do the plotting as well at the end, right? Yeah, I do the plotting here. So you will see the same code here, okay? There's nothing new here. I guess this is something we didn't need to, we know very well, okay? So I guess the thing is to go to this one. This is more fun, right? We'll take a log on y. Okay? We will do a Python code soon. But when the regression, the Python output will tell us there's two number, okay? And because it's still a regression, right? But now we don't use y, but log price, okay? Log of the y. So what we get is, okay, first is how to interpret this intercept, right? The intercept have to be calculated. You take exponential on this one, right? Because you cancel out the log, right? The exponential is 136, a different number, okay? The second is, of course, the most important in this model is not the alpha, right? It's the beta, right? Because you want to use x to explain y, predict y, right? In this case, it's not the distance is not explaining the price, but the price changed, right? So this means that for every mile you away is 13% less expensive, okay? And probably this is still not too easy to see. We will draw a graph to explain, look at it, then you will see more clearly what's going on there, okay? So let's do the Python, okay? And then you will have my idea what we're doing, okay? So what we're going to do is the following. We create another column called log price, which is M.P log, is num.P log, this one, okay? And here you can see it's very simple. With regression model, y and x, the data, the fitted summary, and then we just print it out, okay? So let me quickly do it because I don't think we need to be too slow here. Okay, so for some reason, there's some space here, okay? And we can plot it again, right? We can plot it as well. We can do the same. We can separate it. I can print summary, okay? And then at the end, I also do the plotting together. So everything done in a one single code, okay? Is that okay? Then I just run it. So as I have argued, this free line, right, will give us this. Okay, and as I said before the dinner, we care about this two number here and this number here. Okay, and as we said, what for every mile away is 13% less expensive. The second one is R square, which means that if you employ this model, you explain 20% of it. That means that seems to be fit better, right? Before it's 15, 20. So you want to take a log, right? And the next thing, I think we explained two number there. Okay. Okay. Is to plot this guy. Okay. And maybe I should do another maybe I should do that is better. This is a lot price. Okay. Okay. But I want to look at the raw one. Okay, so this is a good one, but I also want to look at another graph. Okay, this show you the nonlinear one. Okay, so instead of this, I want to show you the NPXP. Maybe call maybe this is fine. Price, I put it right. And my prediction, okay. New. So instead of plotting this price to the log, I want to go back to the normal. Okay, that means that the output is the log version. I want to take the exponential, give back to the normal one. So then I plot this. This you can see is a little bit slightly curved. Okay, so that whether you like it, I don't know, but this is what the model we have. Okay, so before it's like a straight line, but now it's like a little bit more curved. Okay, because this look like a straight line, but now we are predicting the price. Okay, so by allowing this is nonlinear. Is that okay? Because every mile you got is like 30% less. Okay, so that's why it's like this. Okay, it's not. It's like. Is that okay? So that's why the graph, but it's not very obvious, right? But that is what it is. Okay. I think I saw the plot. Okay. Now we want to look at the log distance instead of the distance, all right? And the regression tells you that, okay, the slope is this, intercept this one, right? So this city center is this price, and the slope is 28. Means that what? It means that if you are 1% further away, then it's like $28 less expensive. Okay. So how do we do that? Okay. So there's some trick have to be done here. You will see it's not just take the log of x. The reason being that if log doesn't define when x is close to 0, it's exactly 0. When log is very close to 0, it's very negative. I mean, if you, this is the math problem. If you remember the log idea, if you remember to the log, since you're IT manager, then probably you may not be able to remember a lot of math, but maybe you do. But let me quickly show you the function, right? If this is x, this is log of x, right? Log 1 is 0, if you remember, right? And the line looks like this, right? So it means that when you go to 0, then it's go to infinity, right? And when this is very close to 0, that's not very good. So that's why the code tells you that when it is less than 0.05, what is the number? When it is 0.005, right, this 0.005, and beyond, you just cut here. You just focus on this part, right? So that is what the transformation is doing, right? We cannot transform, we cannot just use log x, right? We have to bound it, right? It's less than, it's so close to the cell center, you just make it like so small, right? Otherwise, the model will just not fit very well. So when you transform log, then you have to be careful like this. Otherwise, your model doesn't look very well. Okay, so there's a trick here. When you too close, then you make, and probably your question is whether which number you should use. Up to you, right? Because this is like 50 meters, right? It's like maybe 100 meters, right? Yeah, 100 meters, right? 0.05 mile, right? It's 50 meters from city center. So I think 50 meters may not make a difference, right? So that is what you do it, okay? And which number you put doesn't really matter, but that's what they're using, okay? And take log, you run the regression, okay? You do the summary, you do the plotting. So that would be something you can do, okay? This is the thing, right? We run the regression, I can print the summary there, okay? And then I can prepare the graph, okay? It's linear graph in this one. And we'll do the nonlinear graph as well. The prediction graph. Okay. It's a graph that you plot. Okay. And this tells you this coefficient we have seen. This is R squared, you will see is even better. So if you think that this is the way the model is, that's helping, right? If you think that, right, it's not the distance itself it matter, it's the percentage it matter, then this is the model we have, right? And this is the graph. It tells me looks like this, right? And this doesn't seem to be very nice because negative doesn't mean a lot. It's a log distance, right? Sorry, this is a log. It's a log distance. Sorry, right? So then in that case, probably you want to look at the x by going back to the normal one, right? So you want to plot, then instead of this, you want to change your plot in this way, right? Y is no problem. You can use the OY, right? But the x we are using, use the distance again, right? There's no problem. We can use that. Then it can compare the distance, right? Then you should run this guy. You will show you this one. The reason this is I should have sort the data first before I do it. Maybe I should sort by x. Okay. The reason that is doesn't look very well because the way that the distance is not. I think I have to sort the distance first. New df is df distance or sort. I think it's like this. I forgot. Sort by, sort ascending. Forget about it. I forgot how to sort. Let's look at it. Sort. And the data frame by column. Sort value by name. Okay. It's okay. It's okay that I forgot, right? I guess. My distance. And that should be fine. I hope. Let's try. So this is a line. Okay. It seems fitting better. All right. So this is the model, right? And R squared is higher. But if you still recall, using this model, nonlinear thing, it become like 20%. Okay. Is that okay? Even though linear regression, you can see we can do a lot of stuff already, right? Looks something amazingly stupid, right? But I mean, we can do a lot of stuff. Okay. Is that okay? Now we go to the very last one. So the plot where, but log, which is very commonly used. Okay. If you learn economics, the beta usually is called elasticity. Okay, elasticity, 弹性. Okay, but anyway, we are not economics, so we'll forget about it. But here, the beta means that if you change the distance by how much percent, how price changes, right? When the regression you show is 1 to 5, right? So it's 1% away, then with 25% less expensive. Okay. So this is the model, right? We have calculated this already, so just run the regression and do the prediction and plot the graph. Okay, so I just copy it and just run it because it is so trivial. I'm not going to do step by step on this one. This is the graph, right? And I just plot. I should use print summary because print looks better. And so this is the graph here. So as I said, this is the important part is the coefficient and R square. The R square you can see, I'm not going to point it out, you should be able to read it, is 33%. So if you purely aiming for R square, that's the best model, right? So means that they are not related directly, but they're related in log sense. Okay, is that clear? What we're doing. Okay, so that log is very frequent way to do transformation. Okay, because very often that is the easiest way to handle how things are related, right? Is that okay? It's the graph. Okay. And before the break, we want to do the star laser, which is going to put you a very nice table, which is production level. Okay. So the star laser, you will not understand what the star means, but we will talk about the star after the dinner. Okay. But we need to install a package. So that's why we'll do pipe install. Okay. How to do that, you just copy this one and open it. What it is actually doing is probably look the pipe install but the Cook Lab cannot will install in this way. So you do it, they will install directly. So once you run it, it will come out like downloading the thing, right? Just wait a little bit. Then you install already just 4 seconds. Once you're done, this is what the star laser is doing. So, but first I would just run the first two lines because that is something I want to show you. The rest is just make it look nicer. Okay. So what I'm doing here is like a little bit crazy code. Okay. From the star glazer, I input the star glazer library. We wonder what it is, but anyway, that's the standard thing. Don't worry. What it's doing is you will combine three regression we have and store it here, and then you want to show it. Okay. And I just show it, then it will show. Okay. So all right. So in this case, you can see it export a table, 4 columns here, right? Telling you all the coefficient you can check, right? R square observation there. This is very nice, and this is table that at the professional level, this is something you will present if you really want to present it in a professional level, right? Because this is all the thing we care, right? Okay. Now, before the break, I want to explain this several line here. The first one, as you can see, you can guess covariate order, which is trying to change the order, okay? Because usually the intercept is in the top. Usually there's not things we care. Actually, we want the intercept at the end, right? The distance, the beginning. So we run this. You can see distance first and log distance second. Is that okay? And the second line of code is because to run the regression is y is the price, log price, price, log price. So I keep call them, and I put 1, 1, 1, 1 because this for one first column, this for one column, this for one column, this for one column. Okay. So if you change it 2, then we would last for 2 columns. It's the length for this one. Okay. And once we do that, you will see how it looks like. Okay. Of course, you can play around with this function. Okay. How come it run with the space? That's weird. Okay. So you put price, log price, price, log price. Okay. And the first thing comes effect, you change the name because usually intercept is not a good name, it's constant. Okay. And the distance, give the name to this one. Then once you did that, this become production level table, right? This is a table that you should present to your boss, to your client, because they don't care about how you name the coefficient, right? They want to know the English, right? So this is the one that actually you would care. And probably you will see there's some star here, which we'll explain after the dinner. And you would aim for the more star, the better. Okay, but we'll explain what the star is. Okay, just to remind you, the more star, the better. Okay, but we'll explain what it is. Okay, you can see by changing the form, the R square change accordingly, and the higher the better. So if you really just aim for R square, this is the best model. And this is the prediction, and then is that okay? Okay. Then the question before we take a break. Any question? I mean, I'll give you the. We'll talk about that after. Not the break, right? After a long break, okay? And after the break, we'll talk about. After the dinner, we'll talk about a few minor things. That's called the piecewise linear spine. We said the following, but we'll talk about it after the break. Is like this. It's very similar to bin scatter. We divide it in 2 parts, one regression and one regression there. 2 regression. Okay. And we also allow square here like this, and we run the similar regression thing. So we are slightly below the schedule, but it's behind the schedule, but it's fine. We're still on time. So, enjoy your dinner, and then we'll come back at 6:30, but not this room, the other room. Okay? So enjoy. I see you later. Bye bye, the people in Zoom. See you at 6:30.